So the first session as is mostly on basics of acoustics. Since all of you are actually engineering graduates, so you have studied acoustics in certain details from the junior class itself. But still, when we start a course, when we start a module, we will be revising the basics of that. കുറച്ച് revise ചെയ്തിട്ട് മുന്നോട്ടേക്ക് പോവാം. അപ്പോൾ we will be moving forward by revising the concept. If you have any questions, you can always unmute yourself and stop. If I can answer, if I will be in a position to answer at that point, I will tell you. Otherwise, I will tell you to be at the end. We will have a question answer session where you can answer the question. Is it okay? Fine. So acoustics actually, what we mean is that acoustics is a science concerned with the production, control, transmission, reception, and effects of sound. So it is all dealing with how sound is produced. The science of acoustics, as it is written already in the slide, it is concerned with the production, control, transmission, reception, and effects of sound. So how sound is produced, how it is controlled, how it is transmitted, what are the various effects of sound, all this we will be learning in this module. So your modules deal with some specialized topic that we will be learning in due course. And today we will start with the basics. So all of you know how actually sound is produced. Can you just put it in the chat box? How do you feel? What are the ways sound can be produced? Can you just respond in the chat box? For example, you can say like hitting a plane surface like a drum, or you stretching a string. So which are the various ways in which sound can be produced? Can you just put some response in the chat box so that I feel that some people are there? Okay, vibrations produce sound. Very good. And then any other response? Vibrations of what type? What vibrates? Any particular shapes or any particular dimensions which you feel produces any vibration, whether it, if you vibrate your hand, whether it produces some type of sound? Pressure change. Okay, pressure change is there, that is fine. Anything else? Vibrations of molecules. Okay, that is also quite good. Vibrations of molecules, but whether vibrations of molecules they produce sound, that we will be seeing. Okay. Okay. So let us see that sound is produced when a body vibrates, as it is written in the slide itself. So, for example, if you take two nails and you tie a rubber band in between the two nails, as it is shown here, and you stretch it, so you'll see that the rubber band vibrates. What is vibration? It moves forward and backward. That is called vibration. And what happens to that? As a result of which sound is produced. Now, whether this vibration anywhere it will produce sound? Yes or no? Answer me. Whether this vibration at any situation, if anything simply vibrates, whether sound will be produced? Can somebody answer? Whether if anything vibrates, vibrations anywhere at any situation, sound will be produced? Yes or no? ഏതെങ്കിലും സിറ്റുവേഷനത്തില് vibration ഉണ്ടെങ്കിൽ sound ആവോ? അതാണ് ചോദ്യം. So whether no, why, where actually Sarita has said that it is no. Any specific small reasons can you give why it will not produce? Sound is produced when a body vibrates. Now there are certain situations where actually sound will be produced, that we will see. And there are certain situations where if you go on vibrating also, no sound will be produced. That also we will see. So, first thing what we have to do is that whether if there is no vibration in any situation, there will be no sound production. That is the first thing which we have to take into account. Next, let us see a vibrating string. Let us try to see how it is producing sound. And when you stretch a string, what are the various ways actually the stretched string oscillates? That also we will be seeing. Just observe this film. Okay, so what are the observations did you get from this particular video? What are the inferences? You saw a guitar which is where there are certain strings which are stretched, and you heard certain sound. So what are the observations which you get from this video? Can you put it in the chat box? Any type of observations, or you want me to play it once again? That also can be done. But what are the observations? എന്തൊക്കെ ഒബ്സർവ് ചെയ്തു ഈ വീഡിയോ ഓടിക്കുന്ന സമയത്തില് കുറച്ച് സ്ട്രിങ്സ് വൈബ്രേറ്റ് ചെയ്തു പിന്നെ അതിലെ സൗണ്ട് വന്നു. അപ്പൊ what are the observations from this video? Let us play the video just once again. Just have a look at it. Yeah. So when some vibrations happen in the string, it makes a sound. Okay, that is fine. Anything else? When strings vibrate in the maximum and minimum amplitude. Okay, one string makes other to vibrate. That's good. Then uh, then there are difference in sound, isn't it? Some string vibrate and make a particular type of sound, whereas some other string. So did you notice about any connection between the type of sound or the pitch of sound and the type of string? The type of string may vary in the material. String may vary in the diameter or certain other characteristics. So did you notice that also? Okay, let us see just once more before. So anyway, there are some observations all of you have made, and this video is of that particular sort. Right. Next. Now I am playing one more video. Try to see the video and say me the inference what you get from there. So what did you observe? What did you realize from this video? Can you say me certain things? Can you put it in the chat? What did you understand, or what did you observe in this video? Again, no sound. The sound is not required. You have observed certain things. That is also enough observation. By observing, you can say me certain inferences which you can make. If you want, I will play it once more. Just observe the video. So can you put up some inferences in your chat box? Can you put some inferences what you observed by observing this video in the chat box? You saw that there are two tuning forks there. Vibration produced without contact. That is very good. Vibration is produced without contact. So how you feel there is no connection? There are connections. So can somebody put some type of explanation that how by striking a tuning fork on the remote side we can make the bob to oscillate? What are the possible explanation for that? Can you just put in the chat box how this is possible? Any Any answers? I am striking a tuning fork at a distance in a remote location, and I see a bob to oscillate in one location. Just observe it once again. Yeah. So vibration transferred without contact, though through air, the amplitude is traveled. Okay, that's a very good inference. So one thing you understand that if for vibration to move and some type of sound which is also produced in the process, and you are making a remote object to vibrate, you need the vibrations to be transferred, and it requires a medium for transfer. This particular now the sound which is getting vibrated in one of the tuning fork, when it comes to the other and makes it vibrate, whose effect you can see on the bob getting now hitting the tuning fork. So this makes us think that this vibration is transferred through the intervening medium. So that is one of the observations which you can make. Okay. So now let us move to the next slide. So here again, actually it requires sound, but I don't know because sound is not getting shared. What happens is that here is a buzzer. So buzzer plays, a sound is produced, and inside this bell jar, what you can see, inside this bell jar, there is air, and you can hear the sound. Now there is a vacuum maker, that is a pump which sucks out the air from inside. So as a result of which, actually, what happens is that inside becomes vacuum. So inside becomes vacuum, and the air is sucked out, and ultimately you will see that you can't hear the sound which is happening inside. I'll just show you. There is some buzzer there, and see just now the person has switched on the vacuum pump, and ultimately now if you go on playing this video, what will happen is that you will see that the intensity of the sound dies out. So intensity of the sound dies out, slowly you can't hear. You can only hear the pump sound. So this is what is shown in the video. So what happens in this case also, what you are seeing is that you require a certain medium for transmission of the sound. So that is what is observed here. Okay. So we stop. We go to the next slide. So for propagation of sound, what is propagation? Put it in the chat box, somebody. What do you understand by propagation? The word propagation. It moves from one location to another. So that is called propagation. So for propagation of sound, a medium is required. So for example, you require a solid medium, sound travels through solid. You require a liquid medium, also sound travels through liquid. Then sound travels to air. But if there is vacuum, sound do not travel. So that is not the case with light that we will see. Sound has this particular property that sound travels only with respect to certain medium. So what are the requisites of the medium through which the sound travels? For actually error-free sound travel without any loss of the quality of sound. So the medium must be elastic. Medium must be elastic in the sense that it should vibrate and it should each time vibrate, it moves from its mean location, it moves away on either side, and ultimately comes back to the mean location. So this is called elasticity. The first point says that the medium must be elastic. So medium must be made up of certain materials which allows you to vibrate, and there is actually restoration of each particle when it moves away from the mean location. That is the first requirement. Second is that the mean must have inertia to store mechanical energy, because the particles in these mediums, they don't actually move around, they just vibrate in one particular location. But the wave moves, so the energy flows. So the energy must be, as the particle, the medium must have inertia to store the mechanical energy so that it will be allowed to move. And third is that the medium should be frictionless. Frictionless means medium, yeah, somebody has written moving. Medium frictionless means actually There should not be friction. When you move in road, you have friction. Without friction, actually, we can't live because our life will be fully stopped. But what happens is that if you have lot of friction in flow of sound or something, what will happen is that it will lose energy. As a result of it, there will be attenuation. So there should not. These are the three main requisites for a medium. Medium must be elastic. Medium has to be elastic. In a medium must have inertia to store mechanical energy. In a monometer, medium should be frictionless. So these are the three requisites for that. So sound cannot travel through vacuum. That is one particular property which you have to imbibe when you deal with acoustics and related phenomena. Now you see how again by vibrations actually we can transfer the vibration, and ultimately by contact we can make other things to vibrate, and which actually produces certain patterns. So let us see. There also no sound is required, only effect you see. So somebody is putting sand on a plate, a normal plate on which actually dry sand is sprinkled. And what happens is that now he's trying to vibrate it with a violin bow. He's moving bow on the side and the hip and vibrate. And your different particles actually they take up a certain shape. So once more, just see. Yeah. So so what I am saying is that just now you saw a effect, all of you saw this effect. Now, can you just give a certain kind of explanation in the chat box of why you saw actually then the pattern getting formed on the surface of the plate when it was actually fully spread out? There was nothing. So why do you feel that certain things occurred? Just try to tell me in the chat box. You saw this effect. Now, don't see the sound. You just see the effect. What happens? So you see that boy is putting some sprinkling some sand on a plate, and when he sprinkle he takes a bow and try to vibrate the plate. All particles in that particular plate vibrate. As a result of it, ultimately they orient in a particular geometry. Yeah. Can anybody just put in the chat box an explanation of what they have seen just now? Why does this happens in this particular way? Okay, we will see to it. I will come back to it. Okay. Now there is one more video again by a we are playing a tuning fork, and we are hitting the tuning fork and bringing it in front of a speaker, and the output of the speaker is taken to an oscilloscope, and we will see how the thing vibration vibrates the speaker, and ultimately how the oscilloscope graph comes up. So just observe that particular video as I be playing that. The tuning fork when it is dipped, tuning fork. Now the slow motion of what is shown. It is the slow motion of what is shown. The vibration is there in the front of which you are putting a CRT while you are putting the tuning fork, you can take a strobe light. Actually, if you play this one, you can see how it is vibrating in a strobe light. So this you can't see without that. Yeah. So how the tuning fork is moving. So now you see how actually by putting the oscilloscope has the motion. So in all these things, actually, what we are trying to demonstrate is that, so whenever you are hitting the tuning fork, it is making a vibration of the surrounding medium, and that vibration is actually striking a speaker, and the output of the speaker is fed into an oscilloscope, which the output variation in the output is shown as a graph in the oscilloscope. So from this particular last video, what inference can you draw? Can you put it in the chat box? ഇത് കണ്ടിട്ട് എന്താ തോന്നാനുണ്ട്? What is the type of vibrations? Because you are seeing the graph which has oscillatory structure. I will put once again. Okay. Now, can you just explain actually what are the observations you made by observing this video? എന്തൊക്കെ വീഡിയോ കണ്ടിട്ട് എന്തൊക്കെ ഒബ്സർവേഷൻസ് നിങ്ങൾ കിട്ടി? Can you just put it in the chat box? You saw that there is an oscilloscope. There is a particular type of graph which is shown in the oscilloscope. You saw that it is through a vibration of a tuning fork through a speaker, and its output is put in the oscilloscope. About what are the inferences? And that the inference ഇത് കണ്ടിട്ട് നിങ്ങൾ തോന്നുന്നു. So can you just put it there? Sensitivity of the sound produced is dependent on the speed of vibration. Okay, that is one observation. What other? Oscillation with a fixed frequency. Oscillation with a fixed frequency. Okay. Okay, one thing you have seen that, see there, it is a periodic type of frequency, means it oscillates, and there is amplitude is somewhat actually same. There is no change in the amplitude. Tuning fork produces oscillation. Okay, tuning fork produces oscillation, and it moves up, and on the either direction it goes up, and then again it comes to the mean position. Good. So these are some of the observations which you have made, and we will, based on all these observations, what we will be modeling the situation. Okay, so what happens when a tuning fork is actually producing? When a tuning fork is hit on a pad or some hard surface, what happens is that it tries to push the ear which is just near the adjacent to the fork. So what happens is that some ear, and when it pushes a volume of air, what will happen is that some of the air will actually close up. They form a closed part that is called actually the compression. And then when they form a closed path, there will be a density loss in some other location, and that is called a rarefaction. Then again we have a compression, a rarefaction, a compression, a rarefaction. So this is the periodicity which you observe when you observe the motion of a tuning fork. The sound is produced when a body vibrates, and the vibration propagates. Vibration is moving forward through compression and rarefaction. Compression is the place where actually the density of the medium becomes high, and rarefaction is the place actually where actually densities are low. In that way, actually, the energy gets transferred from one location to another through compression and rarefaction. Let us see one more type. So here in the previous video, what you saw is that oscillation of a tuning fork and the wave moving through compression and rarefaction. Now let us see a different type of wave production. Let us observe this video. See, one stone is dropped on a pond. Now you see that spherically the wave moves around. This wave moves, wave becomes bigger. Just observe it once again. One stone is dropped, and you can see that the wave is moving away. So here, so what is the difference between the last tuning fork producing a wave and a stone on a pond producing a wave? Can somebody say in the tuning fork, in the chat box, what are the difference in between these two? Tuning fork producing a wave and oscillation producing a type of wave. Okay, what is the difference? What is the difference between the two types of waves? Oh, can somebody, the second is sinusoidal. Okay. What about the first? Longitudinal wave in the form of tuning fork. Okay, longitudinal wave. Fine. We have not spoken about that, but okay, those long we are called, it's called waves which moves through, actually it will be coming in the later slide. Waves which moves through compression and rarefaction, they are called longitudinal waves. Then what about then somebody wrote tuning fork waves are constant amplitude, but this is varying. But amplitude, but what is varying? Akhil there said this is varying. I didn't follow what is varying. Then spherical waves. Okay, what type of waves are actually the waves which you see in the pond? Is it the same type of waves which you see by hitting a tuning fork? What is the difference between these two waves? So there is no difference. So both are having the same way of propagation. Is it correct? Both the waves moving through compression and rarefaction, and waves formed by dropping a stone on the pond. Are they both same type of waves? No difference there. Okay, let us see. We will be analyzing, and maybe we will come to a better conclusion. Let us go to the next slide. So I'll just show you, you just see it once more, and we will go to the next slide. Yeah. Let us see how this, you have seen the compression and rarefaction on the last slide. Now you just see how this wave gets formed. So you have seen the animation, how this particular wave, so there you have seen that the air particles, so they get the, at certain point, it is a concentration of the particular energy. So you get the compression there, and followed by a rarefaction. That is the way actually it moves. Here actually what happens is the disturbance makes that medium, that particular particle on one location to move up and down. So moving up and down, that other one is moving sideways, and this is moving up and down. So there is a difference in mechanism in which actually these two waves are getting produced. So that's what we wanted to know. The first one was one type of wave. Both are actually mechanical. They are required in the material medium. They can be only produced in a material medium. So they are actually mechanical waves. But the waves propagate. In the former case, the particles, now they move along the axis. Along the axis, they oscillate along the axis. And that is the reason actually they produce one type of wave. And they are called actually the longitudinal wave. And the other one which you saw, actually they move up and down. The particles move up and down. So they move perpendicular to the propagation of the waves. So these waves are called actually the transverse waves. So both are mechanical waves as of now. So let us go to the next one. Yes, radial motion is fine. So, okay. So let us have this comparison of both the things what we have seen just now. So the longitudinal waves what we have seen, As we have seen that the density variation occurs, there are compressions and pressure increases at certain locations. There are various actions where density decreases and the pressure is low at those locations. So the speaker sound or the sound of any particular density or the pressure, they goes on varying from one location to another, and that is one way of production of the wave. And another way of production of the wave is that the thing is that the a particle oscillates in the vertical direction. So when it oscillates in the vertical direction, each particle oscillates and it induces an oscillation of the subsequent particle, and the wave as a result moves through it. And that is actually the transverse wave motion. So whenever we speak about wave, there are two types of waves that we have already seen, and I will be showing you the difference again. So whenever a wave moves, there are certain terminology which has to be used. For example, a wave which is moving in a sinusoidal way, as you are saying, the wave which is moving in a sinusoidal way. At the topmost point, it is called crest, and the bottommost point is called tau. So crest and tau. And the distance between the two topmost points, consecutive two topmost points, or the two bottommost points. So these are called the wavelength. So we have the wavelength here, topmost point, one topmost point and next topmost point. The interval between them is the wavelength. Similarly, the bottommost point and the adjacent bottommost point, that interval is also the wavelength. So these are the wavelengths between adjacent tau or adjacent tau, and maximum displacement from the mean position on either side. So this is the mean position, and the maximum displacement from on the top or on the bottom, that is called the amplitude. So we have, for a particular wave, we have the crest, we have the tau, we have the amplitude, we have the wavelength. So these are few of the terminologies which we use with the wave motion. So we have longitudinal waves and transverse waves. So longitudinal waves, as you can see, with a spring. The spring actually, if you have a very big spring and you just press one side, what happens is that the vibration moves from through the spring through compression and rarefaction. So that is a longitudinal wave. But as you saw in the pond actually the particles of water, they oscillate in their mean position in the transverse direction, but the wave propagates horizontally. So that is a transverse wave. So longitudinal waves are those waves in which the particle of the medium moves parallel to the propagation of the wave. So you should understand these 2 points. You should be able to distinguish between these 2 points. So longitudinal waves are those waves in which particle of the medium moves parallel to the propagation of the wave. Sound waves are longitudinal waves. So they move through compression and rarefaction. Sound waves are longitudinal waves. Transverse waves are those waves in which actually particles of the medium moves perpendicular to the direction of the propagation of the wave. So in one case, it is moving parallel to the direction. In another case, it is moving perpendicular to the direction. Ripples formed in the surface of water, they are the transverse waves. So did you now follow what is the difference between longitudinal wave and transverse wave? Though both these waves are generally called mechanical waves or elastic waves, because our medium has to be elastic. If you have a non-elastic medium, the waves will be of different type. So do you understand, all of you have do you understand the difference between the longitudinal and the transverse wave? Yes or no? Sound waves are longitudinal, and transverse wave mechanical equivalent is ripple in water. So did you follow what is the difference between longitudinal waves and the transverse wave? So there is a difference between rippling waves moving on a pond and the waves moving due to a tuning fork. So there is a difference. So did you follow these two? Yes or no? Put it in the chat box. No response? Did you follow? Yes, good. Okay. So now mechanical waves, as we have seen that they move through tuff and crest and tau, and you know the wavelength. Now there is another type of wave which we will deal, but not in this course, but just for a reference and comparison we will be using. They are called electromagnetic waves. So they are actually the transverse wave because propagation electromagnetic waves, as the name suggests, it is a combination of electrical wave and a magnetic wave. It is a combination of that. They move together. And as a result of which actually this particular electromagnetic wave doesn't require a medium for propagation. It can propagate in vacuum. And it has two components in two perpendicular directions. One is having one is a magnetic field, another is a electric field, and they combine together, and the propagation occurs perpendicular to the oscillation. So this is a transverse wave. Electromagnetic waves are transverse waves. Sound waves are actually our longitudinal waves. So this is the difference between an electromagnetic wave and a mechanical wave, such as a sound wave. Is it clear? Is it clear? Yes or no? Respond. Or any questions are there? Anybody? No response? Okay. Again, so let us have a comparison between electromagnetic wave and mechanical wave, like a sound wave and light wave. So what is the comparison between these? Electromagnetic waves are waves that can travel through empty space. They don't require a medium. ഒരു electromagnetic wave propagate ചെയ്യാൻ medium ആവശ്യമില്ല. So they travel without a medium, and that is they are the electromagnetic. Mechanical waves must travel through some form of matter to carry their energy. The matter can be gas, the matter can be liquid, the matter can be solid. Their speed will vary in different forms of matter of different density. So those things are all there. But still, without matter, mechanical waves cannot propagate. But electromagnetic waves are the types of waves which can propagate without any medium. Further, electromagnetic waves are transverse waves because their vibrations are perpendicular to the direction of the propagation. Mechanical waves are waves in which actually the direction of the propagation and the direction of the oscillation, they are all parallel. So particles vibrate about the mean position parallel to the direction of the propagation. So this is the difference between mechanical waves and the electromagnetic waves. Electromagnetic spectrum consists of waves including gamma rays, X-rays, ultraviolet rays, visible light, infrared, microwave, all these parts of the electromagnetic. They have their frequencies and the wavelength vary. But the mechanical waves can either be longitudinal wave or transverse wave. So mechanical waves can be both. As you can see that ripples on a pond are transverse waves, and vibration of a tuning fork are longitudinal waves. So sound waves are longitudinal waves. We have other waves also which are transverse waves. But electromagnetic waves are by default transverse waves because of the propagation mechanism. And then electromagnetic waves can travel through space in vacuum at the speed of light, and in a given medium the speed of wave is constant. For a particular medium the speed is constant. Wave travels very quickly in solid, less quickly through liquid, and very slowest through gases. So these are the comparisons. Velocity, we will see how velocities are calculated, what are the formulations. So up till now, is there any question? Can anybody put in the chat box, or whether they are followed? Any response? I don't see any response. Okay, it is going on fine. Good. Next. So let us now have a classification of different types of waves. We have the mechanical waves, that is which requires a medium. Electromagnetic waves, which do not require a medium. Mechanical waves have two parts. One is longitudinal wave, one is transverse wave. Longitudinal waves example is sound wave. Transverse wave example is water wave. Electromagnetic waves have all the lights like visible light, microwave, infrared, X-ray, ultraviolet, radio waves. So these are the classifications of waves in general. The characteristics of wave motion. So what are the characteristics through which actually we infer that there is a propagation of the wave? What are the characteristics of medium? What are the characteristics of the wave as such? What are the characteristics of the wave motion? So a wave is produced by the periodic disturbance of a point. A wave is produced by the periodic disturbance. The periodic disturbance is in the form of a vibration. When an object vibrates angle, it will produce a wave. A wave is produced by the periodic disturbance. Periodic is very important. It should not produce randomly. It will not produce a particular wave. It should be a periodic. The wave is produced by a periodic disturbance of a point. That is first point. Next is that due to propagation of a wave in a medium, the particle of the medium vibrate about their mean position without leaving their position. That is very important. Particles do not move away from that position. For example, in a water wave, the particles are oscillating in a vertical direction. Wave is propagating through the water. Ripples are going away from the point where actually the stone is dropped. But a particle will be there only. Particle will move in the about the mean position. So due to propagation of wave in a medium, particle of the medium vibrate about their mean position. They vibrate about their mean position. From the central position, they move upward or downward based on the amplitude. They vibrate about their mean position. They don't move away from that position. So that is very important observation of the wave motion. So that was the second point, that due to propagation of the wave in a medium, the particle of the medium vibrate about their mean position. Next, the energy is transferred with a constant speed from one place to another of the medium. Actually, what is transfer? What is wave propagation? Actually, energy is producing. That is the reason one tuning fork kept at a distance makes another tuning fork in a remote location vibrate through the medium. Energy is getting transferred. Similarly, if you have a tuning fork, you are hitting in one position. If you keep a speaker nearby, the speaker, it vibrates the air, and air actually makes the speaker to vibrate, and that vibration in a reverse way can be taken to an oscilloscope. So these things you have seen in the video. So these are the characteristics. So very important that a wave motion is produced by periodic disturbance of a point. Second is that due to propagation of wave in a medium, the particle of the medium vibrate about their mean position without leaving their position. And third is that the energy is transferred with a constant speed from one place to another. Is it clear? Any? Okay, so we have some terminology related to wave motion. So amplitude. So you should know the definitions very well, because now if some questions are given, they are heavily dependent on the way the terms are used. So you should understand each and every term. So what is the amplitude? Amplitude is the maximum displacement of the particle of the medium on either side of the mean position. So the particle is getting displaced in longitudinal wave. It gets displaced in the parallel direction. It moves from the center to either side, parallel direction to the direction of the propagation of the wave. So that is the amplitude. In transverse wave, it moves up and down, perpendicular to the direction, but it moves to a maximum distance. And in idealistic condition, this distance is supposed to be same on the top. So amplitude is the maximum displacement of the particle on either side of the mean position. Its SI unit, standard international unit, is meter. Time period. Period taken by the particle of a medium to complete one vibration is called the time period of the wave. Its SI unit is second. So the time taken by a particle to move from the point, from the mean position to the top, and again come back to the mean position, go bottom, and again come back to the mean position. This full cycle, the time taken for this full cycle, is called the time period. Next is the frequency. Frequency is the number of vibrations made by the particle of the medium in 1 second. So number of vibration which it makes, it can make 10 vibration, 20 vibration, many 1,000 vibrations also, depending on the type of vibration. So vibrations of those particle, oscillator vibrating particle, number of vibrations which it completes in 1 second is called the frequency. It is also defined as the number of waves which pass through a point in 1 second. So if it produces in 1 second so many waves, that many waves will pass through one point in space in 1 second. So that is also if they are giving you that in one from through a point so much waves are passed, you should understand that it's frequency. If they have give you so many waves has passed through a particular points and the period of one wave is so much seconds, then you should be able to calculate the frequency. So its unit is hertz. The frequency is 1 by time period. So that inverse of time per second is called hertz. And then we have the wavelength. The distance traveled by wave in 1 second is called the wave velocity. And wavelength is measured in meter. So that so you have followed all the definitions. Any questions in any of these definitions? Okay, if you have any questions, you should put it in the chat box. Next. Now we have the wave velocity. The distance traveled by wave in 1 second is called the wave velocity. The frequency, what we have seen in the previous slide, the frequency is actually the number of vibrations made by particle in 1 second is called the frequency. And now we are saying that the distance traveled by a wave in 1 second is called the wave velocity. So how it is calculated? It is the velocity with which energy is transferred from one place to another by the wave motion. What is wave velocity? Velocity is the velocity with which actually the energy is transferred from one location to another. So how do we calculate? So you know that the frequency is inverse of time. So frequency is equal to 1 by time. F is equal to 1 by t. Speed is equal to distance by time. So if you put speed as v and distance as lambda is the wavelength, and t as the time period, then you can have the equation, because 1 by t, v is equal to lambda t, or lambda is equal to v into t. That is, wavelength is equal to velocity of the wave into time period of the wave. So this is a very important equation. Again, frequency is the inverse of time. So that is also quite, you should remember, you should not forget that. And if you combine these two, you have v is equal to lambda f. That is, speed of a wave is equal to wavelength of the wave into frequency of the wave. So this is the formulation, how actually the wave is moving and what is the wavelength. If you know a speed and if you know the frequency, you can calculate the wavelength. If you know the speed and the wavelength, you can calculate the frequency. In general, if you know any two, you can calculate the third. Or if they have given you if they have given you time period, you have to calculate the frequency, and then you have to put in the formula to get. So these are actually some of the terminologies which you need to know. So any questions up till now? Any questions? Questions on the? Any response? No response. Should I continue? Okay. Okay. Now we have spoke about the speed. So we know actually how speed is calculated by this particular formulation. Now let us see the speed of sound in different medium. We spoke about the speed of sound. We said that sound requires travel. Now different medium, sound travels in different speed. We saw that sound travels very high with very fast in solid medium. We saw that sound travels in a slower pace in liquid medium. We also saw that sound travels in a much slower pace in gaseous medium. Now, how do you know? The speed of the sound in a medium depends upon the following factors. What are the factors? The factors are elasticity of the medium. Elasticity of the medium, that is one of the things. As I said, what are the characteristics of the medium? We have seen in the first few slides. Elasticity. Elasticity is a very important terminology. Elasticity of the medium. Next is density of the medium. Elasticity of the medium, density of the medium, temperature of the medium. So if the temperature is high, the sound will be traveling at a higher rate because the vibrations will increase accordingly. So in liquid, we have velocity of the sound. If you look at the temperature of the medium, it has to be constant. If the temperature is constant, we have these formulations. In general, actually, velocity of sound is given by square root of elasticity of the medium divided by the density of the medium. This is a very general formula. Velocity of the medium is equal to square root of elasticity of the medium by density of the medium. Now, elasticity is a term which is common because elasticity will vary whether the medium is solid, liquid, or gas. So in a liquid case, we have elasticity is defined by the bulk modulus and density is density. So we have velocity of the sound is equal to square root of the bulk modulus by the density of the liquid. Similarly, in a sound, if it travels from a solid, velocity of the sound in solid is given by the square root of the Young's modulus and the density of the solid. So we have for solid, it is Young's modulus. For liquid, it is bulk modulus. In gases, it is given by square root of gamma. Gamma is the ratio of the specific heat capacities. So gamma into pressure of the gas by density of the gas. So this is the three formulations with which actually we can calculate the velocity of the wave in different mediums. Is it clear? Is it clear? What is not clear, Neetu? Can you just type what you want to know? Which is not clear? What? Gamma. Gamma is the ratio of the specific heat. You have studied heat in your earlier classes, or you know about heat. You know something called specific heat capacity, CP, CV, like that in thermodynamics. When you studied heat, you have the heat capacities, amount of heat required to increase 1 degree centigrade of a particular volume of a material is called, of a particular volume of a gas is called its specific heat. When it is per mole, it is called the specific heat. So the specific heat at constant pressure is said as CP, and specific heat capacity at constant volume is said as CV. Gamma is a ratio of CV by CV. So you don't have to calculate all this. When you deal with acoustic, gamma will be given as a characteristic. It will be provided to you. Actually, for your knowledge, you should know that gamma is the ratio of the specific heat capacity. So Cp by gamma is equal to Cp by Cv. So is it clear? What is the bulk modulus and Young modulus? Okay, bulk modulus, for example, when you studied elasticity of material, or you might have studied, because that is one of the strength of material. One paper is there in your BTech course, in which actually you study the elasticity of the material. So did you all study the strength of material? Strength of material, did you study in your course in previous time whenever you studied? Yes. So when you studied the strength of material, no, CS branch, okay, strength of material. Okay, in plus 2 also it was, in science also it was there. So I will tell you, for example, what is Young's modulus? Let us start with the Young's modulus. I have not prepared the slides for these things because maybe next day I can show you. But now I will tell you that, for example, a object is elastic, whether it is solid, liquid, or gas. An object is elastic when you actually deform the object and it restores back to its original position. That is called the elasticity. So how far you can actually deform the solid so that it will not cross its elastic limit. So that gives a property which is called the Young's modulus. For example, now if you hang a wire from the ceiling with a mass, say 10 kg. So 10 kg, it will stretch. Anyway, weight is there, so it will stretch, but it will not get deformed. If you put 20 kg, it will stretch little more, but it may get deformed at certain point. If you get 100 kg, the wire will snap. So this gives a property to wire. So this will be varying from wires made with different materials. Copper material will have one particular value. Tin will have another value. Aluminum will have another value. So each of these metals or material will have a value, and that gives rise to a particular constant for a particular material, solid material, that is called the Young's modulus. Okay, the strain divided by the stress by strain is equal to constant. So that is the Young's modulus. Stress and strain. Stress is actually amount of force which you have given, and strain is actually the amount of force which through up till which actually it can restore to its initial position. So that defines the Young's modulus. Similarly, we have the volume. In case of a liquid, no, we don't have the length. In solid, we are dealing with the length of the wire. In liquid, we are dealing with a volume, which is area, when we deal with area, and that gives rise to what is called as the bulk modulus. So we have actually the volume of the area that changes, and then it restores back to its original position. Up till that point, how much it changed by giving a shear force on the top surface, it will restore back. So that gives rise to an elastic limit for the liquid, and that is called the bulk modulus. And for gases, actually, we have no gas. We have the specific capacities of the gases. How much how gases expand on heating, how much it will expand when the unit, it will expand and it will get heated by 1 degree centigrade. How much energy is required when it is at a constant pressure? How much energy is required when it is at a constant volume? These energies ratios will give rise to a characteristic for the gas, and that is called the gamma. That is the ratio of the specific capacity. So did you follow that now? Civil and mechanical studied and not others. Okay. Anyway, in plus 2, this chapter is there. Whether you have studied BTech, so you have to study plus 2 science. So in plus 2, elasticity is a very important chapter for all the courses. Okay, for science courses. So you should have studied there. But if you have not studied, now did you follow the explanation? Or we will put in next class, I will put some other slides and I will try to say you, because I have to put the slides before for explaining that. Okay, but did you follow that? If there is a lamp, there are some pictures required which we will be doing it. Okay. Okay, so these are some of the speeds of sound in different types. So you see that the speed of sound, either it is a water means liquid, or air means gas, or no solid means copper, steel. You can see the density, you can understand the density, and you can see the type of material, and you can see the speed of sound in meter per second in different material. You can see copper is 6,420. Steel is 5,900. Beryllium is 12,890. But water is 1,000. So water speed is less. Sound in steel or solid, the speed is more, very high. In copper, it is very high, 6,420. And beryllium, it is much more higher, 12,890 meter per second. But water, it is 1,496. In air, it is 331.45. So you can see. Yeah, somebody has need to say yes, sir. Forgot. Okay, following. We could put it in the PPT. Okay, next time I will be putting it in the PPT. I will start with bulk modulus and all those things. No problem. So you can see that as the material, copper has so much speed in copper or steel or beryllium or aluminum. These are the 4 solid materials. You have the speed in range of say 6,000 to 12,000 meter per second. It is more in such a high range. In water, ethanol, in liquid, no, water and ethanol are liquid. Density is around 1, and the speed is also around 1,496, 1,207. And we have the air, the helium. These two are gaseous. Their density is very low, and their speed is comparatively low compared to others. You can see that it is only 331 in air. And we have other common materials like fat, muscles, cardboards, and all, and their densities are different. So one thing you can see that when a sound is produced, for example, by hitting a particular rod, and if you are putting your ear near that particular rod, how many sounds can you hear? Can anybody say me? When you hit a rod and you put the ear near the rod and you hear the sound, how many sounds you will hear? Can you say me in the chat box? Can you put How many different sounds will you hear? Or how many sounds will you hear? Any answer? 2. So why? What are the 2 sounds? Can you expand it? Very good. You have said, Akhil Dev has said it is 2. Fine. Now, why actually you require, how you will get 2 sounds? Can you elaborate little? From where the second sound will come? Or from where the first sound you will get? Can you say something more? Okay, hissing sound and the sound of the bar. Okay, so the sound of the bar is actually sound traveling through the solid. So that is much faster because solid sound speed is very high, 6,420, 5,940, 12,890. So these are very high speed. So you will get that speed, that sound will come very fast. And after that, what will happen? Sound through the ear will come, which is very slow, which is 331.45 meter per second. So you will hear 2 sound at a particular gap, and that is quite interesting, and that you should know all these types of things will happen there. So factors affecting the speed of sound, we have seen the formulation, we have seen some of the values. Let us see what are the different factors which affects the speed of sound. The density of the sound is inversely proportional to speed of the sound is inversely proportional to square root of density. That we have already seen in the formulation. Speed of the sound V is equal to square root of E by rho. E is the elasticity, rho is the density. So what is the speed of the sound is inversely proportional to rho. That is what is written here. Speed of the sound is inversely proportional to square root of density. That is the first thing. Second thing is that speed of the sound of gas increases with the increase in temperature. That is understood because when you increase the medium's temperature, the particles of the medium has actually a ambient vibration. Already they have, because normally they are in one particular vibration. When you increase the temperature, the particles of that medium they get more energy and they start vibrating more vigorously. And when they start vibrating more vigorously, the speed of the sound of the gas increases. So they can be given by a formula. Velocity of sound at a particular temperature is equal to velocity of the sound at 0 and velocity of this at 0.01 t. T is the change in temperature. So velocity of the sound when it was at temperature T can be calculated by its initial velocity when it was at having a temperature of 0 to the temperature of 0 means 0, it will be in centigrade plus 0.61 T. So this is an approximate toe-fitting formula which works for actually many of the purposes. So that is temperature. But in general, speed of the sound increases with the increase in temperature. So that is there. Then speed of the sound increases with the increase in humidity of the air. The speed of the sound, if the humidity increases, the density will increase, speed will also increase. The speed of the sound increases with the density, speed of the sound increases with the temperature, and speed of the sound is inversely proportional to square root of the density. And then direction of the sound. The speed of the sound increases or decreases according to the direction. If it is in the direction of the wind, and because wind is a movement of the air, and if the sound is produced in a direction where actually the air is moving, then you will get faster the sound. And if it is in the cross direction or in an angle, air is moving in a particular direction and sound is trying to come from a particular direction, so there will be there will be a addition of velocities in both directions, and ultimately it will affect the time in which actually you get this speed. So speed will be, so in general, the speed of the sound depends on the 4 factors. One is density, one is temperature, humidity, and direction of wind. Factors which do not affect the speed of the sound. Previously, I tell you factors which affect the speed of the sound. Now I am saying you factors which do not affect the speed of the sound. The wavelength, effect of wavelength or frequency of the wave. If the wavelength is increased, for example, speed of the sound sound having same other characteristic, but effect of wavelength. If the wavelength is changed, the speed will not get affected in a particular medium, because speed depends on elasticity and the density. Speed is equal to square root of elasticity by density. So if elasticity change, the medium change, there will be a change in speed. If the density change, there will be also an effect in speed. But if the wavelength or frequency change, there will be no effect in speed. Speed will be same. So effect of amplitude change will have no change in the speed. Effect of wavelength or frequency will have no change in the speed. Effect of pressure will have no, because pressure by density, P by rho, in that the P by rho, square root of gamma P by rho we have for the gases. In that P by rho remains constant, because now our various gas laws and all are there. PV is equal to nRT. So P by rho remains constant, and so the effect of pressure on the speed of the sound is nullified. Okay. The speed of the sound in air is about approximately 330. Somebody takes 340, 350. It depends on different where you are actually measuring the speed. So speed of the sound in general is given as 320 to 330 to 340 meter per second. Speed greater than speed of the sound are called supersonic sound. So we have different types of sounds. One is that supersonic, and that is speed of the sound, which is the speed, any speed which is greater than the speed of the sound is called supersonic sound, supersonic speed. Okay. Now, range of sound wave. Range means what frequency to what frequency. This we can hear or we cannot hear. So that is quite important for us, because in acoustics that counts a lot of things. So human ear is able to hear the frequency in the range of 20 hertz. This will be HR. I have typed it as HZ, it will be, not HR. I will correct it. So 20 hertz to 20,000 hertz. I will correct it now itself. It will be 20 hertz to 20,000 hertz. Yeah. So, yes. So the human ear is able to hear in the frequency range of 20 hertz to 20,000 hertz or 20 kilohertz. So this is the range in which actually human beings can hear the audio waves. So the audio wave range of frequency is 20 hertz to 20,000 hertz. Children can hear frequency up to 30 hertz or 30 kilohertz. So it is more than, small children can hear more than an average human. Average human can hear up from 20 hertz to 20,000 hertz. Small children can hear up to 30,000 hertz or 30 kilohertz. Old persons can hear up to only 12 kilohertz. Their sensation gets diminished. So human ear is most effective in the range of 2000 hertz to 3000 hertz, where it can hear even a very feeble sound. If the sound is in this particular range of 2000 hertz to 3000 hertz, it is very sensitive to that, and it can hear much more than what is shown there. So is it clear up till now? Is it clear? All these things, these are basically facts, the range in which actually it's sound. So now, next is, if we continue in that way, there are something called infrasonic sound. The frequency of sound which are less than 20 hertz are referred to as infrasonic sound. Frequency of the sound which are greater than 20 hertz, 20 kilohertz are referred to as ultrasonic sound. So there are some places where actually some living organisms or some places which we also use infrasonic sound, or they use infrasonic sound. There are some living organisms or other places they use ultrasonic sound. So, and we also use for our industrial application ultrasonic sound. Now we have to deal a lot with ultrasonic sound in a part of this particular discussion. So we have infrasonic sound, frequency less than 20 hertz, ultrasonic sound, frequency greater than 20 kilohertz. Animals can produce infrasonic sound as well as ultrasonic sound for their communication. So these are some of the facts which should be known when you deal with various acoustics phenomena. So here we have a slide which shows certain different ranges of frequencies and different types of actually living organisms, living animals which can see. You can see that bat from 1000 hertz to 1,20,000 hertz. Bat can detect. Dolphins from 7,000 to 1,20,000 hertz. Humans from 150 to 150,000 hertz. Cats and dogs. Cats can 60 to 65,000 hertz. Dog from 450 to 1,800, 1,080 hertz. Elephant from 5 to 12,000 hertz. You can see that they can listen from subsonic to ultrasonic. They have a very infrasonic to ultrasonic. So they have a very big range of audible limit compared to a human, where we only have actually range from 20 hertz to 20k hertz. That is 20 hertz to 20,000 hertz. Our is very limited. Our perception of sound is very limited, and in that also we have our high sensitivity is from 2,000 to 3,000 hertz. We don't have other sensitivity. So these our animal kingdom, insects, and aquatic kingdom, they have much broader spectrum of actually sensation in the audio range, as you can see from this slide. So there are various terminologies of infrasounds to ultrasounds. We have bass sound, we have medium sound, we have treble sounds. Treble sound when we, for example, bass sound, medium sound, and a part of treble sound up till say 8,000 hertz is used for frequency of speech, and the range of infrasound to ultrasound, as you know that this is the range of human perception, but we are more actually from 2,000 to 3,000, from this point to actually this point somewhere here. This part only we are very sensitive, other parts we are not. So this is a common thing which this is a common fact which we need to know. So now, based on whatever I have just given you, I will give a small, I will give a small Google form where some quiz questions are there. Try to answer that, then we will move a bit forward. So I will share it in the chat box, and you can also answer that. Okay, so let us go back to the Meet. Let me put it as a message, and it is there. So can all of you, I think the form is there. Can you just give response to that form within say 10 minutes or something, so that we see that how much you got it. Can you start now? We don't leave, we have more to continue. This is just to see that how well you are following the class, so that in similar lines we will be doing. So can you just try to do some multiple choice, and then we will have some more slides where we will be seeing some more things. So for 5-10 minutes, 10 minutes or 15 minutes, just try 10 minutes, you try that form and give some response. So this is over. So now next topic which we will be discussing is the phenomena of echo. So how many of you have experienced echo somewhere or the other? Can you just put it with an yes or some type of annotation? How many of you have experienced echo? The effect of echo somewhere or sometime? Nobody? Yes, experience. Good. Hilltop. Good. This must said Hilltop. Yes. Fine. Good. Very good. So, so in that you might have seen that when you make a sound, what will happen is that you can see the same sound what you have made and one more sound which you have not made. So two sounds, or sometimes you can see multiple sounds. So when you see the two sounds, the first sound actually goes from you. For example, if you clap, the sound goes from you, it hits an obstacle and come back to you. So that is, and you hear it. So that is the phenomenon of echo. So one thing is that the sound should go from you, and your ear should be sensible enough to actually hear it back at the fastest possible time. So there should be a minimum gap between the source, that is you, and the obstacle which is reflecting the sound. So that is one part of it. Second part is that actually sometimes you go on clapping and you see that multiple times you are seeing, it is coming back and again it is going. So it is going on reverberating. So there are reverberations. So if echo effect is actually what happens is that when you sound, the original sounds get also in an obstacle and reflected back, and which is what we call it as echo. So echo has a lot of other effects, or means lot of other uses also, like it has been shown here that there is a receiver, and now it sends out certain waves and it goes and strikes at an obstacle and come up, and that is detected, and it shows how high actually the obstacle is. For example, when a ship moves bottom, the irregularities in the ocean floor, that is found out through echo effect. So, what is an echo? If you try to actually put it in a definite term, an echo is heard only if the distance between the person producing the sound and the rigid obstacle or the reflector is long enough to allow the reflected sound to reach the person at least 0.1 second after the original sound is heard. So why this 0.1 second or 1 by 10th of a second? That is the sensibility with which actually our ear functions. If it is much faster than that, we will not be able to distinguish between the original sound and the reflected sound, because our ear, that is the instrument, our detector is not sensible enough to detect the other sound. So echo is heard only if the distance between the person producing the sound and the rigid obstacle or reflector is long enough to reflect the sound to reach the person at least 0.1 second after the original sound is heard. So this is the definition of the echo. So how do you calculate, for example, sometimes you require what is the minimum distance then, because you know the speed of the sound, approximately you can find out, and you actually know the time which it has taken, because you can time it. You can see that from this, you can have your friend actually to take a stop clock, and as soon as you make a sound, he or she can switch on the stop clock, and when you hear the sound back, automatically you can, that or stop clock can stop. So you have the time, because you can divide that time in half, whatever time you have recorded, and then you can find out the distance. So based on that, velocity is equal to distance traveled by time. Distance travel is distance from you to the obstacle and back. So that is the distance travel. The time taken is recorded by your stop clock, and velocity is known to you. Based on that, if you calculate, you will see that the distance comes as approximately 17 meters. So if it is the distance between the obstacle and the source is 17 meters, a human being can actually experience the effect of echo. So that is what is one thing. So how far the distance should be for getting the echo effect? What are the uses of echo? As we have already seen that we have discussed that echo can actually have lot of effect, in the sense that lot of living organisms like bats, insects, a lot of fishes, aquatic life, they use echo for their maneuvering, their moving, and for avoiding obstacles. They use a lot of things. So these, in fact, our nowadays robotics classes are there. Children also have robotic sensors in their toys, which are obstacle detectors. They detect obstacle and they try to avoid it. So this is one of the very important effects of living beings of ecoism. And other one which we have seen is that these ships, they send out some ultrasonic sound. It gets reflected from certain depth of the ocean, and we know that how bottom under the sea under the surface of the sea, at what depth, what is the obstacle present, so that where there are mountains, where there are valleys under the ocean, which you can see from the top. So we have all these effects studied by using the eco effect. Sonar. Sonar is an instrument which sonar is an acronym for actually sound navigation and ranging, like radar. No, for radio and ranging, we use the radar communication. Sonar is for sound navigation and ranging, and it is also used in actually for detecting obstacle, for detecting the ocean floor, sea floor, for detecting other aspects in the marine. For example, a robot is gone under the ocean, it will use the sonar to actually find out the obstacles surrounding it. So these are actually the various effects of the sonar. What is a sonar? It has a transmitter and which has a receiver. The transmitter transmits to the particular wave, and the reflected waves comes and strikes the receiver, and then they calculate the distance, as we have already seen in the last example of calculating echo. So this is what is all about sonar. Now let us see about vibrations. We have already seen a lot about nature of the waves, the characteristics of the waves. I have already shown you. So there are few types of vibration. So we have also seen that vibrations. We try to express vibration that tuning fork, if it is strike, so it will go on vibrating. But it is a common phenomena that if you strike and if you leave it, ultimately it stops. So why should it stop? Why should it not go on vibrating? That is what is the question. Now here what we will do is that, for example, let us play this video and try to understand what is a free vibration. So let us see this video. You can see there's a animation where actually we can see that a spring is actually oscillating up and down. It is vibrating, and it is trying to, with a chart recorder, it is a pen, it is trying to mark its motion. You can see the amplitude and frequency remains constant in this particular animation as it is shown. It is an animation what is shown. So as the spring goes on oscillating, you are seeing that a constant oscillation is there, constant frequency is there, and amplitude is also constant. So this type of idealistic motion or vibration with a natural frequency is called the free or natural vibration of a body. Okay, so this is the free or natural vibration, where vibration, the amplitude and the frequency of vibration is constant throughout, as we have seen with this video. Next we have another video. Say this one. Let us try to see about the damped vibration. So what is damped vibration? When an object is vibrating, you put a damping force to it. You try to reduce the vibration. In this case, a spring is there and a weight is there, and the spring is moved to make it vibrate, and we are bringing a magnet near that particular moving mass, so that the magnet is trying to retard the vibration. So it will have a damping effect. Let us see how it works. So you can see that this is made to vibrate, and it is vibrating at a quite frequency and amplitude. Now what we are doing is that we have placed a magnet nearby. So this is the magnet which is trying to actually stop. So now if you move the magnet nearby it, it will stop more faster. It will get damped more faster. So this is what is called. So now you see that magnet is nearby and it is actually damped much faster. So it is stopping much faster. So let us play it once more. Just observe it again. So you see that I am vibrating the mass, and it is vibrating at a certain thing, and the vibration is dying down, and slowly it is decaying. So the magnet is at a particular distance from here. This is the magnet. Now this magnet is a damping force, and I am bringing the magnet much nearer to the mass, and again I am actually vibrating the mass. You see that so fast the magnet has stopped. So it has damped. So this is called resistive force is working on the operation, and this is called the damping. The amplitude actually goes on actually decreasing, and this is what is called the damping effect. when you study the damped vibration. So we have seen the free vibration, we have seen the damped vibration, and now forced vibration. Now this is what we have already seen in the previous video. So you are striking one of the tuning fork and so you so this is actually what is called as a forced vibration. You're vibrating one medium and the vibration is energy is transmitted and it actually vibrates another part of the system. So this you are vibrating a system using a certain agency. So that is called as a forced vibration. So vibrations are of three types. So that was this one. So this is a comparison between actually free vibration and forced vibration. So free vibrations are produced when a body is disturbed from its equilibrium position and released. Forced vibrations are produced by an external periodic force, the external periodic force of any frequency. So you are seeing that free vibration is produced is the disturbance from its equilibrium position. That is that, for example, a bob is made to oscillate or a spring is made to vibrate. That is free vibration. And when it is produced by a periodic force, now you are going on striking certain things periodically, you get a forced vibration. Then free vibration, only initial force is required to start the oscillation. Forced vibration, continuously you have to go on. For example, now in a swing, if a baby, one child is actually swinging, to keep them swinging, you have to go on pushing that swing. So that is a forced vibration. The free vibration depends on the natural frequency. The frequency of the forced vibration depends on the frequency of the external periodic force. The energy of the vibration in free vibration it remains constant in absence of forces such as friction. In forced vibration, energy of the body is maintained by constant external periodic force. In free vibration, energy is neither added nor removed to the system. In forced vibration, energy is constantly added to this. Then free vibration oscillation eventually stop depending on the damping force. Forced vibration oscillation stop when the external force is removed. So other requires an external energy and the free vibration, no, it stops through damping. So these are the two aspects of our vibration, free vibration and forced vibration. Next, we will see about resonance. What is resonance? Resonance actually, if you vibrate one particular thing, for example, one tuning fork with its natural frequency, if you strike it, then what happens is that it makes another tuning fork at a particular distance vibrate with its own natural frequency. And that frequency matching is what is called as a resonance. Let us see this. Of to vibrate and this ball to vibrate. So that particular aspect is called resonance. Yeah. So again, we have one more question. That sounds. Where the sound are coming like it, but particular height to get the sound increase that also. velocity of sound using resonance. So this is one of the examples of that. Okay, so what are the conditions for resonance? If the frequency of the periodic force is equal to the natural frequency of a body, then we get the resonance. The resonance, the frequency of the driving force matches the natural frequency. So this is a push. The push and the natural frequency, if they are matching, we get a resonance, and it vibrates at the natural frequency. So that is actually the condition for the resonance. Then lastly today, before we conclude, so regarding resonance, is there any questions from any of you? Did you follow what is resonance? Pre-vibration, post-vibration, and resonance. Did you follow? Pre-vibration, damped vibration, post-vibration, and resonance. What is the difference? Did you follow? Put an yes or a no, or if you have a question, put it in the chat box. Did you follow? Any response? No response? Yes. So we have a response. So now, there are certain characteristics of sound which we need to study in quite detail. They are the loudness, pitch, quality, and timbre, quality or timbre. So intensity of the sound, loudness of the sound, pitch of the sound, quality or timbre. What is loudness? Loudness is distinguishes between loud and feeble sound. So a sound which is quite loud, which has been said loud, we know what is a loud sound, which has been said in a loud way, and what is said in a like a whispering, feeble sound. It mainly depends on the amplitude of the sound. Other factors are the area, vibration, body, distance of the listener from the source. So all these are the factors on which actually loudness depends. High amplitude is loud sound. Low amplitude is a feeble sound. So that is loud. What is pitch? Pitch distinguishes the thriller and flatter sound. So it mainly depends on the frequency of the sound. So loudness depends on the amplitude of the sound. Loudness is on the amplitude, pitch on the frequency. The shorter frequency has a thriller sound, longer frequency has a flatter sound. So that is pitch. What is the quality? Quality or timbre. It distinguishes one sound from another having the same loudness or pitch. If two instruments or two objects have which are vibrating have the same loudness and same pitch, but still there is something which is distinguishing these two, that is the quality or the timbre. Both sound have different sound effects, like the sound of a guitar and the sound of a sitar. We can distinguish which is guitar, which is sitar, but both have same frequency and same amplitude. So that quality is called timbre. So loudness, as we have already said, it depends on the it depends on actually the amplitude. You can see that this has a less amplitude and this has a more amplitude. So this is louder, and this graphics also represents that. Now what happens actually? How is the power of the sound changes? It is somewhat like light. It is somewhat like optics. Optics also. What happens is that we have the source here, and we have the area of the sphere surrounding that particular source. So whatever energy is there emanating from the source, it is getting uniformly distributed on a sphere. So as the sound propagates, the sphere becomes bigger and bigger. So when the sphere becomes bigger, the same power is getting distributed over a bigger area, and so the intensity will vary. So you can see that the power, this area is A. So the total power got distributed over it. Now this is 4A. So the one each area, each section is actually 1/4 of that. No, it got less distributed. Means the same power, because production of the power is same, and area becomes big. So naturally what will happen is that the power per unit area becomes lower. So the intensity becomes lower. So it follows an inverse square law. The the intensity at the surface of the sphere is power by 4 pi r square. Energy twice as far from the source is spread over 4 times the area in 1/4 the intensity. That is very clear from this particular figure. So this is followed, this comparison of the power and the intensity of the sound. When the sound of a particular power is produced at a particular source, how the intensity varies as we move away from the distance. Why? What is the logic? Is it clear? Respond by yes or no. Somebody? Okay. So intensity is equal to P by A. So if we have I is the intensity, P is the power of the sound, A is the area, we have this particular relation. So area is actually pi r square, so it becomes inversely as proportional to square of the radius of the sphere. So sound pressure, small p, sound intensity, capital I, and the distance from the source to the point of observation, small r. So sound intensity is proportional to square of the pressure. Pressure is proportional to the square root of the intensity. So these two relations follow one from the other. Again, intensity is inversely proportional to 1 by r square. As we have seen in the previous slide, intensity is inversely proportional to 1 by r square. The same thing is written here. So power since it is proportional to square root of intensity, power is proportional to 1 by r. So power pressure is proportional to 1 by r. So pressure 2 by pressure 1 is equal to R1 by R2. So we can calculate the pressure, we can calculate the intensity at different distances, and these are the various formulations used for calculation of various things from the given parameters. So that's all for actually the session 1. Do you have any questions before we actually move out? And I will be sending the slide link to Manifold. I will also put it in the chat box. And this is a Google slide. You can always refer to the slide, and they may also give you the recording of the session. If you want, you can hear. And I will also try to address and sit with them and get the sound, whether we can see the sound. If you play this slide in your computer or in your mobile, you will be able to hear all the sound. So any other questions in today's session? Any last part, anything, or did you follow, or do you have any question, or did you follow? Yes or no? Anybody?
Sir, loudness means intensity.
Loudness, no, loudness is actually, which has already been said to you, that no, loudness depends on different factors. Loudness is depending on the amplitude.
Amplitude. Okay.
Yeah. Okay.
Okay.
Okay, so we conclude here today, and they will be informing you when is mostly next week we will have same time the second class of the session. So anyway, I will be I'll be giving you the link of this one in the chat. They will also send you. You can have the link for this presentation that this is given here. And I will be sharing it with them also. So with that, we will conclude this session. Thank you.